Last type of possible input features we have to deal with is categorical variables. So, for example, the type of restaurant, French, Italian, whatever. So this is a categorical variable, gender of an individual, male, female, whatever. So these are usually encoded using what we call one-hot encodings. So we see what's a universe of possible values for the given attribute. So for an attribute with d possible values, then we will need d separate input bits in our input vector, and only one of them will be 1 at any given point in time, and the rest will be 0. Also 1 corresponding, of course, to the input feature value we got. So this works, I mean, mostly well, unless, of course, you have a lot of possible values. For example, if you use in many projects you work on, you might end up with a customer ID or session ID if you're dealing with web data, for example, and these are IDs, so these are categorical value, but they have millions of values, so it would be too much to have 30 million zeros and only one. So as you will see later, one hot encoding in that case will not work very well, and we will have to find another way to deal with this type of categorical vector to avoid this sparsity in the input vector where you have too many zeros and very few ones. So let's look now at the output layers and loss function. So on the output side of the network, the problem of encoding the raw data values into actual values for the output node of the graph is very similar to what we did with the input layer. So for example, if the network is trying to predict the weather variable, different classes, we have, say, 4 classes: sunny, rainy, cloudy, and snowy. We would use one hot encoder with 4 bits. Only one of them will be equal to 1 at any given point in time. What about the prediction y hat? So ideally, it would exactly match the desired value y, and the loss would be 0, and would be done in that case, right? So if we predicted sunny, which is would be represented as a 1, 0, 0, 0, so a vector of 4 elements, and only the first one is 1 because it's sunny. And it turns out that the true value is sunny, so 1, 0, 0, 0, then in that case the error is 0. Now, of course, in practice, this is rarely the case, and that's why you need to train the weights in order to fit the data better. So we need then to think about what an incorrect output value means and how to measure the loss. So in deriving the gradients, we began with the L2, which is the squared error loss function. So this keeps the algebra simple, especially when you're taking derivative, but it's not the only possibility. In fact, for most deep learning applications, it's more common to interpret the output values y hat as probabilities and to use the negative log likelihood as the loss function, exactly as we did with maximum likelihood when we did the logistic regression. So maximum likelihood learning finds the value of w that maximizes the probability of the observed data. And because the log function is monotonic, this is equivalent to maximizing the log likelihood of the data. Okay, so if that's the case, then we're looking for the optimum vector w star that minimizes the sum of the negative log probability for all the training example big N. So in deep learning, typically we talk about minimizing what's called cross entropy loss. Okay, with cross entropy, which is written as h of p and q, this function you see here, is a kind of measure of dissimilarity between two distributions p and q. Okay, so in machine learning, we use this definition, which is the integration of p of z times log q of z dz. So minimizing the cross entropies in H by adjusting the weights W makes the hypothesis agree as closely as possible to the true distribution. So if P is the true distribution we're trying to get and Q is the predicted distribution, by minimizing H, we're trying to get Q to be as much as possible similar to P. Now, because we don't have access to the true data distribution, P star of X and Y, but we only have access to a sample of the data. So we replace the integration with summation. So to minimize the negative log likelihood or cross entropy, we need to be able to interpret the output of the network as a probability. For example, if the network has one output unit with a sigmoid activation function and is learning a Boolean classification, we can interpret the output value directly as a probability. So we can say, for example, if that probability is bigger than 0.5, then it's class 1. If it's less than 0.5, it's the other class 0. So for Boolean classification problems, that's typically what we do, and we just use a sigmoid output layer. Okay, no need for anything more complicated. We just use sigmoid, and then we set a threshold above which the output is classified in a certain way and below which it's classified in another way. Now, for multi-class classification problems like the weather example I gave earlier, or for example, for classifiers used for object recognition, okay, which have, they have to pick between 1,000 different categories, or for natural language models that try to predict the next word in a sentence. Again, they have to pick a word out of a dictionary of 10,000 or tens of thousands of possible words. So for this kind of prediction, we need the network to output a categorical distribution. So if there are d possible answers, it has to output probabilities, probability vector over all d, such that the sum of all the outputs is 1. So this is called a softmax layer. So softmax layer is used for a multi-class classification problem to ensure that the sum of the resulting probability for the entire output vector is 1. This way you can simply say, okay, I'm going to just go with the class that has the highest probability. Okay, so the case element of the softmax is calculated like this, is e to the n value divided by the summation of e to the values for all the vectors. So by construction, the softmax function outputs a vector of non-negative numbers that sum to 1. As usual, the input in k to each of the output nodes will be weighted linear combination of the outputs of the previous layer. So as you can see in our simple network we discussed earlier here, so this could be a softmax activation function G5, which would take the input from the previous layer, which is W, which is 3 5, 0 5, and 4 5. These are the 3 inputs, and then output a vector of probability depending on, in this case, we only have one output, so it's going to output just one value between 0 and 1. But if we had multi-class, then it would output a vector of values between 0 and 1 that sum to 1. There are other output layers that could be used. For example, a mixture, a density layer. This represents the output as a mixture of Gaussian distribution. So such layers predict the relative frequency of each mixture component, the mean of each component, and the variance of each component. So as long as these output values are interpreted correctly by the loss function as defining a probability of the true output value y, then the network will be able to fit the data and the training will converge. Okay, so that concludes our discussion of simple feed-forward network. Now we know all the components, you know how the the hypothesis formulated based on the activation, you know the different types of activation functions, how we encode the input depending if it's continuous, if it's binary, or if it's categorical, and finally what to choose for the output layer if you have a simple classification problem, multi-class classification problem, or just a simple prediction problem, where in that case you wouldn't need to use any softmax or sigmoid activation. You would just use an input, a weighted input of the outputs from the previous layer. Okay, see you in class.